Hello everyone, my name is Taylor Biehn, and today I'm going to be talking about the process I went through for developing my model of my model rocket. So first, a little bit about how a rocket works. A rocket is considered stable when its center of gravity is directly over its center of pressure. However, if these were to shift a little bit, creating an angle between the direction of the nose cone and the direction of flight, well, this is called the angle of attack. And when a rocket experiences this, it creates lift. The reason this is important is because for my model to work, I'm going to have to assume that the rocket is perfectly stable and doesn't experience any lift. Uh, lift the lift coefficient for figuring out how much lift is on the rocket, it can only be determined experimentally through using a wind tunnel. And then the drag coefficient is similar, but the program that I use for creating a rocket called OpenRocket, it can create an approximation of the drag coefficient. However, this is not exact. So here we have a screenshot of what OpenRocket looks like. One of the major things I had to do while going through the process of creating this equation was work with the drag equation here. Since the equations of motion, one component is velocity, using the damping coefficient, I figured that drag can be equated to damping. And however, drag, since it does use velocity, it uses velocity squared. So I had to make sure to incorporate this into my equations of motion when modeling the flight of the rocket. So I wanted to do each stage from the moment the motor ignites to a successful landing. And to do this, I created 3 stages. The first state is from the moment after the rocket or the motor is ignited until it burns out. The second state is it coasting through the air until it reaches apogee and begins to fall down. And then the third state is the parachute deployment. Here are the equations of motion that I developed. I figured I would need 4 state variables because x, the position, is universal. However, there is a different velocity for each state, so there needs to be a velocity for state 1, for state 2, and for state 3. Here are the results of my equations, or in my simulation. And looking at this is very interesting. This first peak here is the moment that the motor burns out. So we get its max velocity, and then it begins to slow down as gravity acts on it. As soon as it passes 0, we see that that lines up with the apogee, or the max height. And then this valley right here, this is the deployment of the parachute, which lines up with the beginning of the straight line. So as the velocity reaches steady state, the rocket will float down at a constant speed. Comparing this to the actual simulation from OpenRocket, we can look at the two side by side and see that there are some discrepancies. Most notably this valley right here, and I would equate this to probably being the time it takes from the ejection charge of the motor to where the parachute actually catches the air. Another discrepancy is the max apogee and max velocity. So I would probably equate all these to the oversimplification that I most likely did, having to remove lift from the equation, also the approximated drag coefficient, as well as the motor change in mass as it burns, and as I mentioned, that delay in the parachute deployment. So overall, I think that this is a good start, but it definitely can be improved. So thank you for your time.